So, we will start with the wherever we left last time, and I think I planned to do buffer delta network analysis now. So, this is basically buffer delta, how this whole thing will be analyzed by creating a simulation model as well as analytical thing, and then we will be comparing it with the delta network which was there, which we had done earlier, and then of course the crossbar. Okay. So, before we do this, there are certain properties which were not evident, but now I think I am opening up one by one all of them. So, first one is a lemma actually which comes from there. So, if you have carefully observed the structure, you can immediately know that this statement is correct, and formally there is no proof required on this. So, this is basically 2 raised power n by 2 raised power n delta network. There is a unique path from each network input link. So, when I am talking about a network input link, it is the whole delta network, the input to that. When I am talking about a switch input link, that is an input to switch in any one of the stage. So, network input and switch input are two different things actually. Similarly, it is true for the output from each network input link to each network output link, which is obvious actually now. So, this was the definition which was given for in general for Banyan network. There has to be exactly one path from each input to each output, and that also means that has to be unique, there are not multiple options. So, this is actually going to be true. From each input to output there will be 2 raised power n possible, each input to all the outputs there will be exactly 2 raised power n paths which are possible, because there are 2 raised power n outputs, and this is obvious because from the first one, this for a binary system, remember I am not talking about A by B crossbars being used in between, but this is also true even for that. So, this case which we are discussing is actually buffer delta is
this path length is constant.
Yeah, path length will be constant from each input to each output, that is true in terms of number of hops. So, it will be exactly equal to number of stages minus 1, those many hops will be required for transmission from any input link to any output link, or whatever n stages which are there. Okay. So, if you keep on expanding their total n stages, each time you are multiplying it by 2. So, from each input you are going to generate exactly 2 raised power n paths, and there are exactly 2 raised power n outputs. There has to be exactly one a path available between each input and output which has to be unique. So, this essentially proofs come from there is by definition. Now, second one is more important observation. This observation I have not actually told earlier. Now, this one is a theorem as per the paper, I am just using the same notation. This says that you consider a switch M is a switch actually in the intermediate stage, and this can be true in general for any kind of delta network, A raised power n by B raised power n delta network also it will be true. Okay, but I am giving a very general statement here. In stage Sk, so stages are actually going from S0, S1 to Sn minus 1. So, that is the way the stages are defined, total n stages. So, remember stages are numbered from 0 to n minus 1, yeah, from source to destination. Since paper is about 2 raised power n, is a binary system, so I am specifying 2 raised power n by 2 raised power n, but this is true in general actually. This statement will be true in general. and this actually helps us in making the estimates, blocking probabilities and all that thing can be estimated from here itself. And as I told, k can take a value, but it will never be equal to n, it is always less than n. Okay. Now what I am writing is an input to a switch, not input to the network. Okay. So when I talk about an input to the switch,
So k should be less than -1.
k is always less than -1, it is never equal to. There has to be exactly n stages. So equivalently there is going to be also an output. So I am writing technically two statements in one statement. So you can replace whatever is there in the bracket also. So I can read let Ix and Iy be two inputs, or I can say let Ox and Oyb be the outputs. Okay. So this I think a very standard thing. This is about the switch. So remember, you take any switch in any stage, there are, if it is 2 to the power n by 2 to the power n, every switch is binary. So there is one top and one bottom, there are two links, input links, similarly there are two output links. So you can call them Ix, Iy and Ox, Oy, whatever it is. And now I think I should draw this. A flat statement is fine, it is clear, but usually what will happen is there will be a switch. I am actually taking for example 8 by 8. So let me make an 8 by 8 and I will give an example with that. And I can take any arbitrary configuration of a delta network. So I can take a shuffle or inverse Bayes, both are fine. So let me take a shuffle. You take any switch from anywhere. You take for example this switch can reach here. So these two inputs can reach to this switch. So I call this set in capital I of x, this is I of x, okay. This will be I of y, so this can reach here, so these two, this set is I of y, okay. Number of inputs to the network which can reach to this particular switch is this. Okay. On the output side similarly, this is 1 and this is one pair, this you can call O of x and this you can call O of y, this is set, and this is smaller O of x, O y, okay. So I am talking about these sets. Let I of x, O of x here, and I of y, O of y be the set. Remember, it is a be the set, it is not individual inputs and it is not the input to the switch, it is input to the network, okay. So that is what it means. To which Ix I need to change the language, will lead actually. So, in this case now important observation, there are 3 points which are important observations. The first thing is your part A, which is the conclusion that your set Ix or Ox and Iy or Oy are disjoint. This set and this set will not have any overlap. This set and this set will also not have any overlap.
Overlap means?
There is nothing common between them, they are disjoint sets, which is obvious because there is always a unique path from each input to each output. So, what if this is the path, this can reach here, and none of these inputs I should be able to reach through this path because there is uniqueness property, path has to be unique. So, I cannot reach to these inputs through any other path except this. So, the first fundamental principle for Banyan network itself ensures that this is true. So, sets will be disjoint, okay. And of course, the cardinality of the set will be how much? You count how many number of stages are there before this. Okay, you are in stage Sk, remember. So, how many stages are there before that? 0, 1, 2, 3, k minus 1, k stages are there. Okay. So, number of elements which will be there in this Ix and Iy both will be 2 raised power k obviously. So, Ix is equal to Iy will be 2 raised power k. That is the first observation, and similarly this should be after k how many stages are there? You have till n minus 1. So, n minus 1 minus k, those many stages are there. So, you must be expanding through that. So, cardinality for that will be 2 raised power n minus 1 minus k. And most important thing, that if you take a set Ix union Iy, any input which is forming, which is from this input from this particular set is a union of 2 sets. Any input in this, if you want to connect it to Ox union Oy, this has to pass through this switch, there is no other option, this has to pass through this switch. So, all members which are from this set, if any one of them have to be connected to any member of this set, the path goes through this particular switch. Okay. That is again intuitive observation, it is going to be true. Okay. And of course, the last one, exactly how many paths will be passing through the switch? This is going to be true here, you can actually put, you have 2 actually, k will be, because this is 0, 1. So, 2 raised power 1 is 2. So, membership is 2, membership is 2. So, 0, 1, 2, which is n minus 1. So, 2 minus 1 is 1. So, again output memberships is 2, 2. So, total number of elements which you can cover in Ix is 2 raised power k, Iy is 2 raised power k. So, total number of input network links which you can reach is 2 raised power k plus 1 obviously. Total number of output links which you can reach from this switch is 2 raised power, again multiply this by 2, n minus 1 minus k. So, when multiply by 2 it is plus 1, so it is n minus k. Total number of possible paths you multiply 2 raised power n plus 1. So, every switch will have these many paths passing through it, 2 raised power n plus 1 paths will be passing through every switch, and total number of paths is 2 raised power n square, because total number of inputs is 2 raised power n, output 2 raised power n, multiply, those are total number of possible paths which can be there. but from each switch this much will be there, and of course you can actually compute how many switches are there. Okay, based on that you multiply by that, that has to be equal to 2 to the power n square.
Could you please repeat? This is not understood, sir. This part.
Okay,
This last one.
at least you understand these many paths will be passing through a switch. So how many switches I can reach from here input side? I can reach this and I can reach this. This is 2 raised power k, this is 2 raised power k. So 2 into 2 raised power k, actually those many I can reach. So which is nothing but 2 raised power k plus 1. On the output side, if you take one link, I will be able to reach 2 raised power n minus 1 k. See, look at the cardinality of the set. So from the other link also I can go to 2 raised power n minus 1 minus k. Total number of output links which I can reach is, multiply this by 2, which is like adding 1 in the exponent. So it is 2 raised power n minus k. So I know these many outputs I can reach through this switch, these many inputs I can reach through this switch, multiply these two, those will be the total paths passing through the switch. So multiply these two, this 2 raised power n plus 1, and this is independent of the stage. Remember, it is independent of the stage, and it is true for, it is going to be same for all switches. It is going to be same for all switches actually. Okay, while total number of possible paths which are existing in a switch is 2 raised power n on this side multiplied by 2 raised power n on this side. So it is 2 raised power 2n, total number of possible paths which can exist. I think this, no, this is, there is a problem here. This is not correct actually, this is not correct. This is for all permutations. All permutations are not permitted.
Network.
Yeah, so it has to be different one. It has to be, because this is 2, each possible thing. Now you take from here, this is one path, second, so there 2 raised power n possible things. So total number of possible paths which are there from this input is how many? 2 raised power n, okay, and total number of inputs are 2 raised power n. So it has to be 2 raised power n into 2 raised power n.
But all possible combinations might not be
Simultaneously may not be permitted, that is a different question. See, that is a simultaneous permutation thing which you are looking at, not the possibility of paths. But technically every input can be connected to every output. But the moment you set up a path, some other paths will not be possible. So we were looking at that when we were using factorial method, we were actually considering that particular fact. That is, suppose there is no connection being set when I set this path to here. So there has to be at least one path which will get occupied, and I can do it in n possible ways. I can set up the connection, but possible paths I am talking about, possible paths or connect the wires or possible ways in which paths can exist, that is 2 raised power n square only. So it is 2 raised power n square n2, 2 raised power 2n. So each switch, actually the number of paths which can pass through, see, all of them cannot, there can be exactly 2 paths which are permitted out of these. Possible paths which is passing through a switch is only 2 raised power n plus 1, but only two paths will be permitted at any point of time, depending on whether switch is in cross or bar state. If it is in cross state, then also 2 will be permitted, in bar also 2 will be permitted, remaining combinations will not be allowed. But possibility of all paths is 2 raised power n plus 1, and total number of switches here is 2 raised power n whole thing divided by 2, 2 raised power n minus 1. So 2 raised power n plus 1 multiplied by 2 raised power n minus 1 will give you this only, 2 raised power n 2n actually, if you look at all things in the stage. So all possible number of paths passing through a stage has to be equal to this, which has to be constant. Important thing, number of paths which a switch can pass through a switch is independent of a stage. You take whichever switch in whichever stage, it is same. So this fact actually was not explicitly told earlier. Okay. So this comes from this. Now before we go for this buffered system, we actually have to make certain assumptions. So without which we cannot hold. So let me come to the assumptions now.
This will be true for Banyan networks also. Then these observations will be true for Banyan networks also.
Yeah, it's true for Banyan networks. Only thing, Banyan network you cannot have that uniform tag for reaching to an output. For same output, depending on input, you might require a different tag. Delta networks, a common tag is good enough, which defines the output port.
So what's the difference between exactly Banyan network and Delta network, except tag?
There is no other difference. It's only tag which is the difference.
The tag is only for the step routing.
Yeah, but then if you are using Banyan, what I did in Banyan network, I always said in any stage, the packets which are coming in, they have to come from the same output ID of the switches in the previous stage. So in this switch, for example, if you look at this, I am getting 0, I am also getting a 0.
This is from Delta network.
This is a delta. So this is also a subclass of a Banyan. Na? If this condition you don't impose, it's a Banyan network. So it is not a clause or anything. There is exactly one unique path which is available. So for 2 raised power n by 2 raised power n built using 2 by 2, you require n stages obviously for Banyan network. There will be exactly one path by design. So first one is a basic assumption, I think, which is obvious, that each packet which is going to arrive at the network input link at here. So we are not bothered about there is going to be an interface card or not. We are simply saying there is going to be a packet which will contain a label and a payload, and label will identify to which output the packet has to go. Okay. So that is the first and foremost assumption, which is obvious, so I am not writing it. So I just simply say each packet at input consists of a label plus payload. We call it also a tag. Usually interface processor will insert this tag. So I am not bothered about the interface processor. Usually you will look at the IP packet header and then based on that decide what tag has to be inserted after looking at routing table. So this being done, there is an assumption here, and of course this is important, condition of maximum loading exists. So condition of maximum loading actually means at the input there will be a buffer, only one packet can be stored here. So at the input, only at the input of the input links of the network, not of the switches I am talking about. Okay. So sometimes it is possible that buffers will not be occupied here, but at the input there is exactly one buffer, one packet. The moment this buffer becomes empty, immediately a packet will be coming. That is a maximum loading condition. So traffic is always available at the input to be pushed into the switching matrix.
Each switcher or the whole Delta network?
Whole network I am talking about, not each switch.
Only one, sir. There will be only one buffer for the input.
One buffer for each input port.
Each input port, sir.
There are buffers inside also in buffer delta.
So we are saying 1 into 2 to the power of n minus 1 buffers are there. 2 to the power of n.
2 to the power n buffers at this point, 2 to the power n buffers here, 2 to the power n buffers here for a buffer delta situation. If it is an unbuffered delta, the earlier case, then these buffers are not existing, buffers are only here. That is a maximum loading condition when P will be equal to 1 technically. And of course, the output link, if there is a packet, it will be almost instantaneously taken out. Okay, buffer will be emptied immediately. Ultimately packet is hopping is being read one after another, it is not a crossbar. So, the moment it comes here, it is immediately taken out, there is no readout time is 0. So, that is another assumption which is taken. In fact, interesting part is when the buffers are going to be here. So, you will find that sometimes buffers are here, but you cannot fill this buffer even if it is empty, because these two guys made a conflict and they both wanted to come here. So, one of them was pushed here, other one was left in the buffer. So, one buffer emptied, so packet came in, but no packet actually moved here in this buffer. So, here the probability that buffer will be occupied is always equal to 1. As you move across, the probability that buffer will be occupied will start reducing from 1 to a smaller value as stage is increased. And ultimately, if I know what is the buffer occupancy probability here, that is a throughput performance under maximum loading condition. Well, that is what we are going to do ultimately. Okay. And of course, the third one is an important thing, that all input links are independent of each other and they independently choose an output port, there is no correlation, every packet coming in is independent. So, that is an important thing. Now, this is something new. At every switch, when two packets come in, you have to detect whether to which outgoing port it has to go by looking at the tag. A digit in the tag has to be looked, and once you have identified which outgoing port, it has to be read out. So, usually there will be a buffer here, it means there is going to be a one packet buffer and it has to be read out. Okay. So, if they both want to go here, there is a selection time and then after that it will be passed, it will be read out actually to the outgoing port, it will go to the next buffer. Unbuffered delta technically means if there is a conflict, one of them will be simply dropped. So, fresh packet is always allowed to come in, that is what it means. A buffer delta, you will keep it there, you will not allow other packet to come in. So, what happens is unbuffered delta technically means if you decide this packet has to go, you simply transmit, do not bother about whether the buffer ahead is empty or not empty, because if there is a conflict, one of them will anyway will be dropped. At every stage this is what is going to happen. Buffer delta will not allow this, it will keep the packet in the buffer, it will not drop it. So, the packet from the previous stage cannot come.
Sir, how to choose this in case of a conflict, which packet will?
Here assumption is a random choice, here it is a random choice. And remember, the arrival rates here are also independent. Why they are independent? Because the input set Ix and Iy, they are disjoint, and I have assumed that all inputs here are independent of each other. So, take off the independent inputs, so take one set, take another set, and if they are disjoint sets, so these inputs also have to be independent of each other. So, this independence actually holds through all the stages, because this independence of this Ix and Iy set is true for all switches in all stages, is a consequence of that actually.
So, in buffer delta, sir, we are not allowing the packet to be dropped in the intermediate stages.
Yes.
That means that the buffer will keep on filling if we move towards left, and that means the packet will be dropped at input stage then.
I am using maximum loading condition. There is some infinite buffer at the input, I am not bothered. Yeah. So, you are not bothered about that. There is always a packet available when the buffer empties. That is a maximum loading condition. So, maximum loading condition may happen at your utilization factor, which is when it is less than 1. It is possible, but inside you will have unit buffers in that case. So, delay now consists of this is basically independent arrivals at the input and equiprobable selection of output. The D part is, there are two parts, one is known as T select, there are two times, other one is known as t pass. So this is the time when the selection is made after reading the tag, and second time it is t pass, that is 1 t slot actually. And when the minimum delay will happen is when I am using unbuffered delta. If there are two packets, if there is a conflict, one of them is permitted, other one is dropped. So how much time will take from input to output? So this t select plus t pass multiplied by number of stages, that is a minimum delay which a packet can suffer. So this multiplied by n is min d, or the minimum delay in this case.
Sir, what is T pass actually?
T pass is in a switch. When the packets are there, you have to first of all select to which outgoing port these have to go.
That is under T select.
That time taken is T select, and after that the packets will be passed or dropped, actually one of the two. So that is a time in which the packet will be transmitted out. It is like a store and forward. It is not circuit switching, remember. You have to receive the complete packet, then you have to transmit. After reception, you do not start the transmission immediately. You have to make some decision. So on time actually scale, if I put a time scale like this, so you receive a packet, packet reception is completed here. You will take some time to decide, this is T select, and then you will start transmitting the packet, packet is finished. So this is your T pass. Usually we will assume one of them to be 0 actually ultimately for doing the simulation thing, but real life this is the way it is. See, most of this cannot be analyzed with closed form solutions, it has to be done through simulation actually, but for certain cases certain kind of bounds can at least be estimated, that is possible. So in case of when the network is without buffering, all packets will be delivered in this case, or they will either be dropped actually. One of the two things will happen, either they will pass through in this time or they will be dropped, they will be lost.
Sir, the passage time will be less than from one stage to other stage, or the difference itself is?
Which one? The difference, that is the propagation time, that is going to be small actually. So you can assume it to be a horizontal line almost, it is like a horizontal line, okay, it is like a horizontal line. This is one first previous stage, next stage. So unbuffered, this is what is going to happen, but for buffering, this switch now can be modeled as a Petri net. Okay. So Petri net model will be of this kind. Again, I think some of you have not read Petri net, so I will try to explain what is it because each one of you have not done a course on communication networks earlier. Okay. So Petri net is basically you have some kind of token buffers, and this is basically used for finite state machine depiction, is for that thing. So if there is a token here and I connect it to something called where the decision firing will take place. Okay. So for example, there are two tokens. So this firing can only take place when both tokens are available. If there is only one token, there is no firing possible actually. And when firing happens, all the tokens from on the input side will get consumed, and they will fill up the tokens on all outgoing sides. And we then put certain restrictions. This is what I will do. For example, then I can put a token here. I can put a token here, for example. So if there were two tokens here, there were no tokens. So condition has been met for the firing, and I will end up in getting two tokens here, which then can be further connected. I can also now put a time here, is known as delayed firing actually. I can put a timed Petri net we call it. So when the condition is satisfied for firing, after that there will be a delay, and after that delay only the token will be generated on the outgoing token holders. So, I can build up I think lot of machines in this fashion. So, I had done earlier I think one of the data link control protocol was implemented this way in the previous semester. So, that is basically the fundamental, but now let us build up the switch. Because I am now doing backward propagation of the buffer status. In a buffer delta, if the buffer is busy, I have to tell the previous stage that buffer is busy, you cannot send any packet to me. Packet only can come if the buffer is empty. So, I have to build up the pattern net model for understanding this. So, actual implementation, it means there is going to be a backward signal path also, which will give the status back. If you do actual implementation of buffer delta, otherwise you cannot do that actually. So, I will use two colors here, one for the data and one for the control path. Okay. So, data will contain now two paths, and this is known as input buffer. There is nothing like an output buffer, because output buffer for this switch is nothing but the input buffer of the switch in the next stage. Okay. Input buffer in the next stage is nothing but the output buffer for this. Okay. And then of course, if a packet comes in, there is some time which it takes for making the selection, which outgoing port it has to go. Okay. Once the packet is here in the buffer, this will cause what we call a selection process. So, there will be a, we call it T select will be the period for this. Now, this packet can go to up as well as can go to down, both ways. So, there will be, I have to now build up technically 4 things. After this time T select, depending on, now the firing will depend on, outcome of firing will depend on the bit which is controlling the routing. If that bit says it has to go to bottom, so this will, the both of them, so one of them will not fire, because here I am doing a selection process. So, whatever is the outgoing buffer which is connected, outgoing token holder which is connected to this particular firing edge will not get a token, because that will depend on the selection thing bit, it is a bit control. So, that is not explicitly mentioned, but that is how actually it is. So, this in turn will then this is known as output request buffer. So, they are requesting the output. If this has to go to here, this will actually be fired up. Okay, this will not be, that is decided by bit. If the bit controlled is 0, it will come here, if it is 1, it will come here, if it is 0, it will go here, it will come 1, it will come here. Okay. So, there is output request buffer, there will be 4 of them. So, one of these will always be active, not both. Similarly, one of these will be active, not both of them, or other way around. No, it is possible both of them can be active. Both of them can be on at any point of time. If there is only a conflict, then only one of them will be. So, you will keep on holding and try next time. If there is a conflict, basically what happens, this is 0 and this is 0, both of them will come here, both of them should fire up, I should actually hold up output request buffer. I think both models are possible. Okay, I will explain this. This is one particular part. Now, this is the input buffer for the next switch in the next stage. Okay. and usually I will have the status which will be coming here. We call it a successor buffer empty flag. If this buffer is empty, this will be set actually immediately. So, they are linked together. There will be two such things. Okay, I will use this color for arrows are important here. Okay. Same thing, this will be for the previous stage. Whatever you are seeing here is for the next stage switch. Similar thing also has to happen here. There is a backward propagation of the control signal because of that. So, for example, if this guy is selected, the upper one, it will pass the packet to the outgoing thing, and this buffer will become empty actually in that case. So, I have to get back this, will come here. In fact, this should be highlighted with red. And of course, if this one passes through instead of this one, so this token will get consumed and I will set this particular flag in this case. Okay. And then they will talk back further. So, backward propagation is there. So, this is T select and only one of them should be there actually, both of them cannot be there. So, that I think is taken care of by this conflict resolution T select. So, if both of them want to go to the top, both of them will come here, only one of them will be fired up, other one cannot be. So, it will remain there as it is in that state. Okay. And after T select, this output request will be there and this will pass through when this condition is met, and as this packet is going out, this buffer status flag will be reset and this can then communicate back. So, new packet can come from again in this direction. Usually T pass is a time in which the whole packet will be passed on to this buffer. This will also include usually this signal time. Backward propagation signal time can be included in that. It does not matter, every time when you are forwarding a packet, signal is coming back. So, include both of them, combining them does not make any impact. So, that is how it will be actually modeled as, this is a pattern net model for the buffer delta system actually, for a 2 by 2. If it is n by n, then it is of course going to be tricky. Now, what you are going to analyze when you want to do a performance analysis? So, in any network, one of the most important thing which you need to do is throughput performance. So, you have to analyze it under maximum loading condition. Ideally, if it is possible, you keep on changing your input arrival rate or input probability of getting a packet in a slot and then do the analysis. Second thing which is important is known as turnaround time. So, this time is nothing but the time difference between two instants. The first instant is when the packet is arriving at the input port or input link of the network, not of the switch, of the network, and when it reaches to the output link of the network, the gap between that is what is your turnaround time. So, minimum turnaround time will be min d or minimum delay. Okay. Similarly, maximum throughput will be what you will get with a buffered delta, unbuffered delta actually. So, that is a benchmark which can be taken, and based on that you can create a normalization of whatever exactly you will compute. So, I think I will close now, and then we have to do now basically unbuffered delta analysis first. So, this actually I could have done it earlier also, but I am doing it now, along with then crossbar, and then of course the analysis of this buffer delta system, and then we can basically make the comparison of the three.